Hello everyone, welcome to the another very important session in which we will be discussing some more important questions and the concepts of condensed matter physics. So I hope that the discussion which we will be doing today in this session will be getting clear to all of you. But in case if there will be any doubt anybody will have, you can surely let me know about it, guys. We will try to consider those points then. And I will be starting the discussion about the most important questions and the concepts for our upcoming exam. Give me a second. Okay. I am just gonna check out like is everything all right and clear, and if yes, we will be ready to start the discussion then. So let me just quickly check the session and then we are ready to start. Also guys, the current slide you can see right now is regarding the latest like features, benefits you will be getting if you will take the Unacademy Plus or the Iconic subscription. So in that case, what are the benefits you will be getting, okay, and how it will be helping you to take your preparation to the next level, all that has been shown here on the screen. Other than that guys, now even the important notes are available on the learning app which will be helping you to take your preparation to the next level. Done. So important notes are available, even the live classes of well structured and well planned courses by the top educators are available on the learning app, which will be helping you to learn new tips and tricks and to get ready for the upcoming exam by knowing about this thing, that what are the most important things and what you can expect to be there in your upcoming exam, from which section they can ask the questions, and how you need to do the preparation. So everything will be getting clear to you. So if you are the one, or even if any of your friends want to take the subscription, so in that case you can share this information with them to let them know about this important information, that even in upcoming days so many new courses by the top educators will be starting on Unacademy, which will be helping everyone to join the courses and the classes from the beginning, and even some of the new courses have started recently, so if you want to join them you can even take the subscription, okay, and you will be able to check out the recordings of the sessions as well. uh I am just gonna check out, guys, is it the same thing? No. Okay, now it's correct. Done. Okay, so we are good to start the discussion, guys. Here are a few more slides. Let me just quickly show you. This is about the Unacademy learning app. This is about the session. This is something about me, and this is about the community feature we are having on Unacademy. Now we are ready to start the discussion about the condensed matter physics part. So again, what we will do, we will be taking the important questions along with the concepts, and then we will be keep on talking about those questions, that how you can solve them, what will be the best way to solve these questions, how in the less time you can solve these questions, and what is the best approach to solve it, right? So that's what we can consider. Now let's take our first question right now, and whatever type of questions are the most expected ones, I will try to include them here, right? So let's take the first question right now. If you will have any doubt anywhere, you can let me know. Tell me one more thing, guys. Do you want me to start the discussion with the questions or with the concepts? What would you prefer? Hello, Sakshi. Do you want to know some concepts first or directly the questions? Because we can start the discussion anyway. If you're the one like who thinks, oh, I want to start the discussion about like I want to know about the discussion first before going to the question, so we can even do that. If you think like you want to work on the question, we can even do that. Okay, Sakshi, if you would prefer the concept first, let me just start the discussion about the concept then. Hello, Deepika. Guys, do you want me to talk about some of the theories like the free electron theory? Because from that section, we are gonna have the Fermi energy, Fermi velocity, and Fermi momentum, Fermi temperature, or density of states. So all these questions you get in the exam, and these are based on the free electron theory. So what do you think? Should we start the discussion about that? And do you want to know about it? If yes, I can start the discussion from this particular topic, because once we will complete it, we can also take the previous year questions and we can try to cover up these things in this session today. Okay? Let's start that part, because that will cover up your one particular section. Okay, and even that section is the one from where you can expect the questions in the exam, so it's good to consider. Or the other choices, if you want, I can talk about the vibrations in the 1D lattice or lattice vibration topic basically. Now tell me in the comment section what you want me to start the discussion with. Do you want me to cover up the lattice vibration today in the session? Do you want me to cover up the free electron theory? Now, free electron theory part will help you to understand in 1D, 2D, 3D cases how to use the Fermi wave vector, Fermi energy, Fermi temperature, Fermi and about the optical branches, the acoustical branches and all that. So, which one you would prefer to learn? What about others? Is there any particular choice? Both are equally important for the exam. Anybody is having any choice or anything we can start with? Anything? Okay, let's just start with the lattice vibration. For the other topic, we will try to plan other session too. Okay, like both are equally important. Both are good topics. Both are gonna be like the one we should consider and cover up. So we can take any one of them. So right now we are gonna go with this. But if anybody would say like, no, I want to learn that one, I can even start with that. And the way I will talk about is that everybody will be able to understand and get it, okay, even if somebody is preparing it for the first time. So not so much theory will be involved, not so much those things will be involved which are not needed while working on the questions, but everything will be what you need when you will work on the questions, and what is needed to solve the questions, right? So that's what we will focus on. Now, in this case, what will happen? Our first topic will be vibrations of 1D monoatomic lattice. One-dimensional monoatomic lattice. Now, what you will consider when you are going to talk about vibrations of 1D monoatomic lattice, you are going to consider a one-dimensional chain of atoms. So you are assuming like there is a chain of atoms, and that's in 1D. Okay. Now, since we are talking about the vibration, we will say, okay, these atoms are gonna vibrate. Done. Now, in this case, if they will be vibrating, then they will also get displaced, okay, from their actual position. So, which means when they are in equilibrium, this is the thing I have shown you right now, when the atoms are in equilibrium, right? Sandeep, we will try to complete most of the topics in our different sessions, because there are some of the sessions I'm gonna have here on Unacademy Live CSIR UGC Net, and for this month, like, all the sessions are almost planned. So they are going to be on various subjects and not just on one subject sequence wise, okay, because you will get a chance to learn different tips and tricks, concepts from various subjects. You will not just be sticking to one particular subject at a time. So that's how the sessions have been planned. While in the Unacademy Plus courses, I'm gonna have those detailed discussions too. Other than that, the special sessions on Unacademy Learning app are even there, which are going to be free live sessions as well. So you can join those sessions. In every session, you will learn something different, something new, okay? Or that will be helping you this way. Now guys, in this case, when the atom is gonna vibrate, then it will get displaced from its actual position. So it may move here this side, or you can show it on the other side. So from its equilibrium position, how the atoms are getting displaced from their actual position, that's what we are going to show in the second line. Okay, so that is when they have vibrating from their actual position or equilibrium position. So how they have been displaced from their equilibrium or the mean position, that's what we are showing in our second figure. Okay, and you can see the displacement in terms of distance from their actual position. Now we are also considering the masses of the atoms is m, as well as they are connected with each other with the spring, and the spring is having the spring constant, okay, and you are gonna consider that spring constant to be c. Sometimes we take it as k, sometimes we take it as c, because k is also the notation for the wave vector. So any of these notations can be taken, either k or c. So right now I'm taking it as c as the spring constant. Okay. Now the distance between any of the two consecutive atoms also we need to define. And let's say that distance is what? That's going to be a. C is what? That is the spring constant. Any doubt to anyone till now? Because we will be using these notations in further discussion. So we had the one-dimensional chain of atoms. The atoms are connected with the spring. The spring constant is c, and other than that, the masses of the atoms is m, and the distance between the two consecutive atoms is a. We also call this as the lattice parameter or lattice constant a. Please tell me if there is anybody having any doubt till now. We can talk about it. But once you got this part, what is the next thing? So we are going to talk about the dependency of force on the spring constant, as well as how much distance has been traveled. So you know, as per the Hooke's law, it will be F is equal to K times X. As we use this formula for the spring system as well, that force, restoring force means what? If there is a spring and there is a mass connected to it, let's say you are shifting this mass this side, means it will get stretched, okay? Then the restoring force try to bring this mass back to its actual position, and that's why we call that force to be restoring force. This force depend on this vector, that how much you have displaced it. If you displaced it more, it means more restoring force will be acting. So F is directly proportional to the displacement from its equilibrium or the mean position. More the displacement, more the force you need to bring it back to its actual position. Less displacement, less force is needed to bring it back to the actual position, right? So once you got that, that is gonna be the Hooke's law statement, and you use these basic relations, basic rules, and you form some equation here. We don't need to go in depth of the derivation part, so I'm gonna let you know exactly what is your dispersion relation here. Okay, all that those steps you will take to write force. Then you will say, okay, I know that force is equal to ma, and then I know that a is what, d2 x over dt square. Okay, because dx over dt is what, that's your velocity, and change in velocity over time, that's gonna be acceleration. So you use all these formulae, and once you use them, you are going to get the dispersion relation, because here you are gonna include the velocity, okay, the one we have written just now. So that gives you the dispersion relation. Dispersion relation is basically the omega versus k relation. But the derivation steps are not that much needed, and anytime whenever you will be working on the questions, you are not going to do the derivation. So you need to know this, which is omega square is equal to 4c over m sine square ka over 2. K is what? The wave vector here. A is what? That is the lattice constant. C is what? That is the spring constant. And omega is going to be your angular velocity. Okay. Now, in this case, what will happen? In this case, if you are just going to consider this relation, omega versus k relation, in condensed matter physics, we call it dispersion relation. Sometimes you can also have E versus K relation, because you know E is equal to h nu, and then you can relate it with the omega. Okay, and somewhere you may also get the term written as angular frequency, right? Now, dispersion relation. Once you got this, now in this case you have to consider the simplification of this relation, which will give you omega is equal to square root 4c over m sine ka over 2, right? And in this case, what will happen? Then you will consider that the wave vector, which is k, it is going to have different values at different places and the positions. Okay, now we are going to apply the conditions on it. There is a possibility to have the low frequency, or you can say the large wavelength. Let me just write it here, the condition we are going to consider first. For large or long wavelength range. Do you know how the wave vector k will get effect? Anybody knows how the wavelength and the wave vector are related to each other? So you need to know k is equal to 2 pi over lambda. Lambda is the wavelength, k is the wave vector. Done? So in this case, if we are saying the wavelength is long, means it is having the larger value. Okay? So in this case, what will happen? In this case, the k will be small, right? And for k to be small, what will be the next thing you will have to consider here? That is going to be, do you know, sine theta for the smaller theta is approximately equal to theta. Everybody knows about it or no? Sine theta for the smaller theta will be approximately equal to theta. This is mathematical condition we are going to use here. Firstly, we said, okay, for long wavelength condition, what will happen? K will be small. Why? Because k is equal to 2 pi by lambda. Very good, Sakshi. Because that is inversely proportional to the wavelength, right? So k is small. And now for small k, your angle of sine, which is k over 2, will also be small. For smaller theta, you take sine theta approximately equal to theta, because you also know sine 0 is having the value 0. So that gives you an idea. Smaller theta, sine theta is approximately equal to theta only. So that will give you omega is equal to square root 4c over m and ka over 2. Can I write it this way? Done? And when you are just going to simplify it, 2 and 2 will get cancelled out, because 4, when it will come out of the square root, it will give you 2 there. So it will give you root c by m and just Ka. This is your omega, which is angular frequency you had. Please tell me, is this clear to everyone now? So whenever you will have the long wavelength, can you tell me your frequency will be less or higher frequency, or the less value of frequency you will have for the long wavelength? Because question can be asked by relating it with frequency too, right? Instead of wavelength. So we need to know that. Tell me. What do you think? For long wavelength, will you have the larger frequency or smaller frequency? Very good, Snehashish. Very good, Deepika. Very good. Very good, Snehashish. That's going to be low frequency. Long wavelength means low frequency, right? So this condition also we should know how they are going to be related. Very good, Sakshi. Now, once you understood that, okay, in the 1D monoatomic lattice case, what is the main dispersion relation? Either call it this one or this one, both are same. And how to find the expression for omega for the long wavelength, low frequency, or the small k condition. So all that is clear. But now what we are going to do, we are going to find the group velocity and the phase velocity. In condensed matter physics, these two are very important. So d omega over dk is the formula for group velocity, and omega over k is the formula for phase velocity. Can you please tell me whether the group velocity and phase velocity for your long wavelength condition is equal or not equal to each other? Very good, Deepika. Will these two values will be equal or not equal for this? For long wavelength condition, we are doing this discussion right now. The discussion which we will do can be used as a fact in your questions later on. So that's why it's important for you to know, like, oh, actually, yeah, this is what I have studied. For this particular condition, we are going to have this thing getting satisfied. And the much more you will get familiar with the facts, it will help you to save your time in the exam by directly using them in the questions. So tell me, for long wavelength, group velocity and phase velocity are equal or not equal? Omega is root c by m Ka. Just have a look at this. So are you going to get Vg is equal to, when I'm differentiating it with respect to k, I'm going to get this. When I'm just dividing it with respect like by k, I'm getting this. So I'm going to have Vg is equal to Vp. That is, group velocity is equal to the phase velocity, right? And this is going to be the condition for the non-dispersive medium. So whenever your group velocity is equal to the phase velocity, it tells you that the medium is non-dispersive medium, or it is behaving as a non-dispersive medium. So this is the name we give to the medium when it is having its group velocity and the phase velocity is equal to each other. Okay, very good, everyone. So here you can see, and you learned the fact that in case of long wavelength range, okay, or whenever we will have lower the frequency or a small value of k, then our medium will be behaving as a non-dispersive medium. That's the fact. Okay, in your net exam, gate exam, anywhere it can help you, but it's important for you to know. And how you reach to that conclusion, that's what we just observed here. Is that clear to everyone? If yes, we are ready to talk about second point. So the medium is behaving as a non-dispersive medium now. Done? Ready for the second point? So we just now talked about the long wavelength condition. Let's talk about the small wavelength, but other values will change accordingly. So now, if you will have the smaller value of wavelength, okay, or you can say shorter the wavelength, accordingly the frequency and the wave vector will change. So frequency will be what? Large or high frequency. And since you know k is equal to 2 pi over lambda, so shorter wavelength means k large. Done? Now, in this case, what will happen? In this case, your expression is not going to change. It will remain as it is, which is omega is equal to root 4c over m sine ka over 2. Earlier it has changed because you had the condition for smaller theta in case of sine theta, how it gives you the value. Okay. But for this particular situation, you are not gonna have any such formula for sine. Okay. So you're gonna just keep it as it is. In this case also, we will just find the value of group velocity, which is d omega over dk, and it will give you a over 2 root 4c by m and cos ka over 2, right? And this is how you got the group velocity. What about the phase velocity? You are just gonna have 1 over k square root 4c over m and then sine ka over 2. So in this case, did you get the group velocity and the phase velocity is equal to each other? No, you didn't get them. So when these two are not equal to each other, so the medium is behaving as dispersive medium. Now, it's not only about the lattice vibration, it is in general too. Maybe not everybody will be familiar already with this concept, like, oh, when they are saying dispersive medium, that means they want to tell me that the group and the phase velocities are not equal to each other, right? So this is what your dispersive medium. And if they use the word in the question, the medium is non-dispersive medium, so they want to tell you that, oh, okay, the group and the phase velocities are equal to each other. Okay, so you also learned the dispersive and non-dispersive medium. Does it make sense now? And everybody is gonna get it? Clear? If still there is any doubt anybody is gonna have, just let me know. But if it is clear, we are ready to talk about the next point. Excuse me. Okay, guys. So this was about 1D monoatomic lattice. Monoatomic means when you had one atom present at each lattice point. Diatomic means when you will have two atoms together present at each lattice point. That will be diatomic. Now, it's the time to learn about the optical branch and acoustical branch. How many of you know about it? If you know, tell me something about that, whatever you know. If you don't know, I'm gonna make it clear to you in a way like you will never forget that and you will be 100% sure about, oh, this is optical, this is acoustical. But that's a funny way. It's not like something serious. Anybody is gonna say something about it? If yes, let me know. If no, I'm gonna let you know. Just I'll wait for some time for someone's reply. Somebody will say something, that's great. If nobody will say anything, I'll tell you. Okay guys, great. Let's go over it. So as I've told you or explained you the dispersion relation, which was omega versus k relation, right? That means omega is having k in its expression. So that means you can simply observe. Oh, that's great, Snehashish. That's one of the things we can say, right? But I'm gonna tell you the conditions regarding the condensed matter physics, and along with that, like whichever you will be able to use in these type of questions. Okay, but that's too great. Now, so here I'm gonna say that when I'm gonna plug in the value of k as 0 here, what value of omega I will get. So when I'm gonna plug in, let's say k is equal to 0 in my dispersion relation, which is omega versus k relation. Let's say I got omega as non-zero. Okay, I put k 0 in the dispersion relation and I'm gonna get omega as well 0. So this is the condition. The first one is for optical and second one is for acoustical branch. Now, what is funny about this thing? Funny thing about this thing. So let's introduce that fun fact about it. Do you want to know? Means if you want to know fun fact, I can tell you. But if you are not interested in that fun fact, then let's keep it this much. But the fun fact I was talking about, which will help you to always be 100% sure about the conditions and you will never forget and mismatch them, so that's the fun fact I was talking about. But if you want to know, only then I will tell you. Okay, done. So let's talk about it. You have to count the initial alphabet, okay, and the number of zeros in total. 1, 2. But in this case, how many maximum zeros are possible? Because first one is A already, only first alphabet you have to count, no other, only O, A. So it can just have maximum 2, which will be from other 2, right? And it already has 2. So you can have the equal number of zeros here. Otherwise, one will have more zeros and another one will have less zeros. So when you talk about optical branch, you are already gonna enter k is equal to 0. So one more 0 you introduced, right? 2 zeros you already have now. So the third one should be non-zero. Did you get it? In acoustical, k 0, but it is having one less 0 till now as per the first alphabet condition. So omega must be 0. Now again, it's like not so much serious thing, but it's something which will always keep you like the idea you will have, the clarity you will have about it, like okay, this is the condition. Again, optical, k is equal to 0 and omega is non-zero. Okay, I should not write optical here. I'll write the condition once again. Okay guys, k is equal to 0, you got omega is equal to 0. Can you tell me it's optical or acoustical? Randomly I have written it. I'm saying there is an expression of omega versus k. Okay, I put k 0 there, I got omega 0. Is it optical or acoustical? Very good, Sakshi. Very good, Deepika. Because you don't want one more 0. That's the optical. You don't want that. Already 2 zeros you have. Okay? And 2 zeros are enough zeros. We never prefer the 3 zeros anywhere, right? Like, if you're thinking about the amount, you may. But in terms of like in general, it's 2 zeros are enough. 100, 200, 300. Okay? So normally 200 marks, 100 marks out of that you get. Then I will say k is equal to 0 you entered, but you got omega non-zero. Can you tell me which branch it is? Optical or acoustical? Very good, Sakshi and Deepika, for previous question answer. Do you want more zeros? Yes. 1 0 is less right now. The second one is non-zero. You would want one more 0. So how you will say? It's optical. Very good, Sakshi. That's great. Very good, Snehashish. That's great. Very good, Deepika. That's great. So do you need more zeros? If yes, optical. Do you need more zeros? If no, acoustical. Did you get it now? And you will feel the importance of this concept and the fun fact when you will work on the questions or when I'm going to do more discussion further. So you will see the importance of it. Done? Now for this question, this part of the discussion, can you tell me, are you getting the just optical branch or just acoustical branch, or are you getting the optical and acoustical both the branches? You have the choice to observe this. To observe this, let me just use a different color. To observe this final omega expression, and to observe this. Okay, how many we had? 3. Yeah, we had this one too. So third one is this one, second one is this one, and first one is this. You have to put the k values there and you need to tell me that are all these acoustical or are all these optical. Very good, Mahesh. Let's wait for others reply too. Or these can be optical and acoustical mixture as well. I mean, some of them is optical, some of them is acoustical. So you just have to check it out. All optical, all acoustical, mixture of optical, acoustical, in which case then it is optical and in which case then it is acoustical out of this. Because we have to draw the graph now, omega versus k graph, and that's important. Tell me. What do you think? Mahesh has answered. What about others? Sine 0 is 0. I'm getting omega 0. Do I need more zeros? No, I already have 2 zeros. Now it will be acoustical. Here I'm going to plug in k is equal to 0. Then I'm getting omega 0. That means I already have 2 zeros. Do I need more zeros? No, I don't. Acoustical. Third case. K is equal to 0. Sine 0 is 0. Omega is also 0. 2 zeros I have. Do I need more zeros? No. Acoustical. So I got all of them acoustical. Right? Very good, Mahesh. Very good, Snehashish. So let me know everybody is getting all these 3 conditions to be acoustical. The main condition, the long wavelength, the short wavelength, all conditions, right? So now you learned how to check which branch is existing there. Is it acoustical branch or is it optical branch? Let's plot omega versus k graph. Omega should be on y-axis or k should be on y-axis? What do you think? You know y is the function of x. So where you take x and where you take y. Same way, omega is the function of what? K. So where you will take omega and where you will take k. Omega should be on y-axis or x-axis? Waiting. Omega x ky, omega y, okay. See, y you show here and y is equal to function of x. Means y depends on x. So you show x here. Now this time omega is the main thing like y and the omega is the function of k. Means its expression is in terms of k. So k here. Done? Everybody is getting it? Very good, Sakshi. Snehashish, is that clear? Done? So, because I know that this is the point where when you will work on the questions and the further you will try to plot the things, you may have confusion. That's why I talked about it this way. Okay, that you will finalize what is going to be on which axis. So let's plot it, guys. Here I'm gonna draw it. Now, can you tell me, this point is the point where k is 0, right? So can you tell me at k is equal to 0, what is your group velocity you will have? Or you can say just omega value you will have in general. At k is equal to 0, what is omega? It's 0, right? And also if I will talk about these points like this one and this one, so here I can talk about the brilliant zones. So brilliant zones are related to you talk about 2 type of lattices. One is the direct lattice, another one is the reciprocal lattice. In case of reciprocal lattice, we further have the introduction to the brilliant zones. Okay. So brilliant zones have, the first brilliant zone is having the boundary at plus minus pi by a. And those values of plus minus pi by a is for k values. This is the boundary of first brilliant zone. Okay. So this is minus pi by a and this is plus pi by a for the k values. And that is the boundary of first brilliant zone as well. So now at minus pi by a, what will be your k value? Let's check it out. So when you will put the k minus pi by a, you will get negative value of something like root 4c over m. Is it so? Because this will become 1 and root 4c over m. That's the positive value or negative. You can just have a look at that too. Other than that, you are going to consider the plus pi by a. So again, you will be able to get this value. Means you have the magnitude equal for both the conditions. And your type of graph you will have like it, if you will just take in between values from 0 to pi by a, you will find it to be decreasing this way, okay, or increasing further this way. So your graph for the acoustical branch is this. And since we talked about the condition when k is 0 and omega will be 0 in the acoustical branch, so always your acoustical branch is going to have this type of graph, because k 0, omega 0 here. So then it gives you the graph joined with the x-axis or the k-axis. Does it make sense to everyone now? Done? And this point is known as the center of the Brillouin zone. You don't have to make it like a circle. I was just talking about it, so I just shown you by highlighting that point. It's like center of the Brillouin zone, because center of Brillouin zone is also where? At 0. But first Brillouin zone boundary is where? Plus minus pi by a. Brillouin zone. Okay, this is the boundary of the first Brillouin zone. Any doubt till this point to anyone? If yes, just let me know. We'll talk about that point. But if everything is clear, we'll go over the next point. Done? Can you tell me what is the maximum value of omega you got? What is the maximum value of omega? From here, when you put pi by a at this place. What is the maximum value of omega you got? That root 4c over m. Is that clear? And that is top of the band, bottom of the band. Now I would like to explain one more thing. Very good, Sakshi. In the questions, you will observe this part. They will sometimes say at the bottom of the band. Very good, Snehashish. Near the bottom of the band. Any differences there in these two statements? Any difference? Near the bottom, at the bottom. Any difference? Yes? What about others? Is there any difference? So answer will surely be yes, right? Why? All these points, this one, like not all of them, but these points near, but this point at the bottom, right? Which is exactly at the bottom, right? Very good, Snehashish. Very good, Sakshi. So at the bottom of the band, k is exactly equal to 0. But near the bottom of the band, you will always use the condition k is tending to 0. It's about to be 0, but it's not equal to 0 till now. So at the bottom, k is equal to 0. Near the bottom, k is tending to 0. Does it make sense? And everybody is gonna get it. If still there is any doubt anybody is gonna have, you can just let me know. But this point is gonna help you to get the right answers for the questions, because mostly students avoid this point near at, they exactly put just k0, okay, but it's not 0 all the time. Near just tend to 0, not equal to 0. Clear? Next thing. Now we are going to start the discussion. This was your vibration in 1D monoatomic lattice. So you can see what you have to prepare from this section. Any question from previous year's NET exam, GATE exam, you can check out. If it is from this section, you are ready to do it. Okay, we will also take some examples after completing a little more discussion about the concept part, and just have a look at this. So what you prepared once, dispersion relation, then you talked about long wavelength condition, short wavelength condition, in which case it was working in the as a non-dispersive medium, in which case it was working as a dispersive medium. Then you learnt about the acoustical and optical branches, how to identify what are the conditions, how many zeros you need, that's the fun fact there. and the condition which will help you to work on the questions. Are you ready to learn about the vibrations of 1D diatomic lattice now? Ready? Again the branches will come back. Again you will observe the conditions, and now you will answer because you learned it now. Okay, ready? One dimensional but diatomic means at each lattice point two atoms will be there now. Okay. Done. Now each lattice point will have two atoms, but will always the masses of atoms for both the atoms will be same? No. We will take the generalized case, means we are taking the masses to be unequal, and that will make us ready to even modify the condition. And further, if they will give us same masses, we can just put m1 is equal to m2. But right now we are taking different masses because that's the general case. General means you can do modifications in it. But if I will talk about equal masses, you may get confused in the final expression that what should be m1, what should be m2. But when you will go with m1, m2 separately, you will not get confused. So here this time we will have two masses, okay, two atoms at each lattice point. So let's say this is m1, this is m2. Oh, then we can't observe m1, m2 written clearly. m1, m2, m1, m2, it will keep on going, right? Because the lattice is not restricted to a particular reason, it will be extended up to infinity. So you can see diatomic lattice, two atoms at each lattice point we will have. Now the lattice constant, you will find it by considering the distance or separation between the two consecutive similar kind of atoms. Means it's not good, because if you are taking it to be your beginning point, so this will be your other beginning point. If you are taking m1 to be beginning point, means a starting point, then other m1 will be your starting point for the next lattice point, right? So that's why from wherever you want to measure, but consecutive similar atoms, between them the distance will be lattice constant. Okay. Other conditions like the C's lattice, C's the spring constant, all that will be remaining same. Okay. But one thing I'm gonna assume is m1 mass atom, even we can show it to be a little bit smaller. Okay, the inner area we are just gonna make it small right now. That is a smaller mass atom, means m1 is less than m2. That's what we are assuming, right? Now if in any case they will give you second atom is greater, so according, like second atom is smaller, so accordingly just wherever m1 we will have, you can write m2, wherever we will have m2 you can write m1, just interchange those things. Okay, now in this case we will write the dispersion relation first of all, because that's what is important for us, and that's going to be the spring constant times 1 over m1 plus 1 over m2 plus minus c square root 1 over m1 plus 1 over m2 square minus 4 sine square ka over 2 and divided by m1 m2. It seems to be lengthy, but we are having this. And can you see I have taken plus and minus 2 signs there? Why? Because maybe we will have two different branches existing this time. That's what we will observe later on. We can't finalize it right now, but we will observe it later on. So this is your dispersion relation in case of 1D diatomic lattice. C 1 over m1 plus 1 over m2 plus minus c square root 1 over m1 plus 1 over m2 square minus 4 sine square ka over 2 divided by m1 m2. If there is any doubt, just let me know. If it is clear, that's great. So this is what our dispersion relation. Okay, even to make it more clear to you, I can show you plus minus here as well, that okay, both conditions I have taken here. But if you don't want to write it, you can just simply write it this way as well. Okay, So once you got the dispersion relation, this is the only thing. If you will even memorize the first condition, okay. Oh, I'm gonna come to that point, Snehashish. I'm gonna talk about that too. Dispersion relation, right? Now, in this case, should I tell you what is the plus sign for? Okay, you will tell me. Plug in the K0, you will get sine 0 is 0. And tell me when your omega is equal to 0 and when your omega is non-zero, tell me positive sign when you are taking. Is it acoustical branch or is it optical branch? What we do, we enter K value 0 and we see like omega is 0 or non-zero. So you tell me whether positive sign is corresponding to optical branch or acoustical branch. Very good, Snehashish. That's great. What about others? Positive sign, optical, acoustical. Very good, Sakshi. That's great. Right, Raveen? Omega is non-zero means, do you want more zeros? No, you want more zeros because omega is non-zero, right? So one more zero you want, and that's optical. Yeah, that is O, but looks like 0, so that's what we are considering. Done. And for the negative sign, is it optical or acoustical? Very good, Deepika. That's great. For negative sign, when you plug in K0, then what it gives you, and for negative sign, is it optical or is it acoustical? So that's the meaning of positive and negative sign you had here. Okay, and you are the one who is identifying and telling me like, okay, this is optical, this is acoustical, because you know it very well that when it is optical and when it is acoustical, as we talked about the conditions. Very good, Sakshi. That's great. So I can even mention it here. But positive negative sign is not something which is making it optical or acoustical. That's the condition we studied. K0, omega 0, acoustical. K0, omega non-zero, optical. So that's the condition making it clear. Raveen, did you attend the session from the beginning, like when I was talking about the branches? Did you attend that section of the session? Raveen, were you there? I just want to know that, like, did you attend the session from the starting or no? Then again, I will repeat if you didn't attend that part. But if you attended, I will just relate it with that. Were you there? If no, I can let you know. Okay, so do you know when K is 0 and omega is non-zero, what kind of branch it is representing? Okay, great. Do you know what it is representing then? When you enter K0? Okay, that's great. Yeah, tell me, when you enter K0 and omega, you get non-zero. So what is this branch? Do you know that? If you know, you can just mention it. If you don't know, I will let you know. So it will represent the optical branch. Okay. When you enter K0 and omega is also equal to 0, then it represents acoustical branch, right? This is the fun fact about it. Even I have already explained. So that will be helping you to never ever make mistake in this part. So in this session itself, we talked about that fun fact as well. Since you attended it from the starting, I think you already know it. So in this case, if you will observe, when you are entering K0, sine 0 is 0, right? So you are having the positive sign. Then your omega, overall omega, because these two terms will get added. So overall omega for the positive sign is non-zero. That means when it is non-zero, it's optical branch. Clear? And when you are entering K0, but you are taking negative sign there, then your overall value becomes 0 because that gets cancelled out. So then it is acoustical branch. Raveen, still is there any doubt? If yes, let me know. I can just try to make it clear to you, but if it is getting clear, then that's great. Mention your doubt if there is any. And if it is clear, then that's great. Tell me, is there any doubt? Okay guys, optical branch means I'm simply gonna write omega positive. Guys, we will have the session for a few more minutes now. You can say 15-20 minutes more. And today we are gonna have the session this way. Actually, the previous one was planned today morning, but it was not there today morning, okay, because of some technical reasons and all. So we had before this. And again, let's see tomorrow morning session. Otherwise, like, we can have together tomorrow again. So like, they have been planned separately, one morning, one evening time. But due to some technical issue, we have this way, right? Now, in this case, optical branch expression is simply omega positive square is equal to C1 over M1 plus 1 over M2 plus C square root 1 over M1 plus 1 over M2 square minus 4 sine square Ka over 2 divided by M1, M2. Is this clear to everyone? Now for the optical branch, we are just going to consider the long wavelength and the short wavelength conditions. And then we are going to observe at the boundary of brilliant zone and the like other conditions again. Okay, the first brilliant zone boundary, the center of the brilliant zone. So when you will consider the long wavelength, in this case, what will happen? You already know low frequency and also smaller k value because k is equal to 2 pi by lambda, right? Now in this case, k will be tending to 0, not equal to 0, because you don't know how long it is exactly. So your k value tending to 0 will give you omega positive square is equal to, or you can directly write omega positive value 2c over m1, 1 over m1 plus 1 over m2. So omega positive will exactly be just the square root of this, right? And when you got it, this is what, when you are considering k is equal to 0, I can take both the conditions when k is equal to 0 and k is not equal to 0 but tending to 0. So both conditions we can take here. So when you will take k is tending to 0, then your sine square Ka will replaced with what? Ka by 2 square, and accordingly we'll write the expression. But if k is equal to 0, then this condition you are taking. Done? So any of them we can consider while tending to 0. So that will be near the bottom of the band, at the bottom of the band. Okay, that's what will let you know whether it should be tending to 0 or equal to 0. But we can write both expressions because we already know what we have to do. How the sine square Ka over 2 term will change. Done? The expression written here is for k equal to 0. But if you want to write it for tending 0, just write this term completely without sine square part but with k over 2 square. Now if I will talk about the another condition, that's going to be Give me a second. So another condition you are gonna have is the short wavelength condition, right? And when you will consider the short wavelength condition means high frequency. And this, since this is the discussion going on about the optical branch, so in that case, what will happen? In case of optical branch, you are just going to consider omega positive square. And what it will give you? It will be giving you just C 1 over M1 plus 1 over M2 and plus C square root 1 over M1 square, okay, plus 1 over M2 square. And when you are going to consider the expansion of 1 over m1 plus 1 over m2 square, so it will give you 2 over m1 plus m2. And other than that, since you are going to take sine theta, where theta is maximum this time, k is large. So at larger theta, what is the maximum sine value which is possible? What is the maximum value of sine you can have? Is that 1? The maximum value possible. So if I will relate that condition here, I can also write sine square theta for sine 90 degrees equal to 1, which is my maximum value we can have. And larger k means we are taking pi by a, okay, plus minus pi by a, the Brillouin zone boundaries. So that will help you to get this, which is going to be your 4 over m1 m2 after considering sine 90 is equal to 1. Once you consider this part, you will get the negative sign of 2 upon m1 m2. So it will give you c 1 over m1 plus 1 over m2 plus c, can you get this as 1 over m1 minus 1 over m2 square. Tell me if in case there is anybody having any doubt, we can consider it then. But if it is getting clear, that's great. When you will do this calculation and simplify it, tell me, are you going to get simply the omega positive is equal to square root 2c over m1. And this is where? This is at k is equal to plus minus pi by a. That is the first Brillouin zone boundary. Please tell me, does it make sense and everybody is going to get it or no? Same thing we will have to do for the acoustical branch as well. Okay, for acoustical branch, we are just going to take the negative sign in between. But for optical, we were just taking the positive sign in between. Okay, let's quickly just consider acoustical branch as well. And let's observe what will happen there in that case. And then we'll just see if we can take 1 or 2 questions and if everybody will be ready to solve the question. Otherwise, we will be ending the session then. Okay, guys. Now, second, we are going to talk about acoustical branch. Means I will take the negative sign. First condition, you are going to take the long wavelength. And when you are considering the long wavelength, your k value will be smaller. Either you can take it tending to 0 or k is exactly equal to 0, right? So any one of these things you can consider there. So depending on whether you are taking it tending to 0 or you are taking it equal to 0, you will be getting your expression then. So if I'm going to write it, k tending to 0. So sine theta will be approximately equal to theta, because you know for a smaller theta, sine theta is approximately equal to theta. So my value of omega negative square will be c 1 over m1 plus 1 over m2 minus c square root 1 over m1 plus 1 over m2 square minus k square a square over m1 m2. So what I have done, I have simply replaced this one with what? Ka over 2 square. Okay, so that 2 square will be 4, 4 will get cancelled out, so I just have k square a square, right? Now once you have this part here, what next? The next thing is the simplification step. Can we take the 1 over m1 plus 1 over m2 along with c common, and then we will have 1 minus. There is one question from the previous year's CSIR net exam we had, which requires these simplification steps which we are doing right now. So focus on this part. Maybe next time again they can give you some similar kind of question and you have to focus on such kind of simplification then. m1 m2 over m1 plus m2. I'll give you some time to observe it and tell me whether this calculation clear to everyone or no, what I have done right now. I have taken this term common, so at place of this I had 1, okay? Then from this part I have taken this common and c also common. So square root, here also I had 1 because I have already taken it common. It was the square, so it went outside the square root, so it was just a normal term like this. Now next thing, 1 minus this, but this one was not present here, so I will multiply and divide with it to take it overall common from the square root. So I got this as the LCM part. Everybody is getting this calculation? If yes, I'll change the slide. Clear? Is it clear? Clear, 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 clear. Done? Okay, great. Now what next we will do? We are gonna use the expansion here, because you know, if you are having the power half, like even the square root you can remove and you can show that square root as the power half term, right? And when you do the series expansion, so in that case you bring this half here at this place before k square a square and you just simplify. So that simplification I'll do here now. C 1 over m1 plus 1 over m2, 1 minus 1 plus 1 over 2 k square a square m1 m2. So this half is here because you remove the square root and you just try to do its expansion. m1 plus m2 square. Let me know whether it's getting clear or no. That's great. Times half k square a square m1 m2 divided by m1 plus m2 square. That's it. This will get cancelled out with one of these. This and this will cancelled out with this. Omega negative is ka c over 2m1 plus m2 to the power half. Here omega is directly proportional to k. Okay, this is what you got. And if you can recall, in case of monoatomic lattice also you got the ka term, right? So omega was proportional to k there as well, if you can recall that. Done? If we are going to talk about the next thing now, that is for the high frequency or short wavelength case, what will happen? Let's talk about that too. So guys, in this particular case which we are discussing, which is acoustical branch, let's talk about the short wavelength or larger k value, right? Done? So if you're going to consider the short wavelength condition, in that case your frequency will be high and your k value will be large, which is the wave vector. So then your omega negative square will be equal to c 1 over m1 plus 1 over m2 minus c square root 1 over m1 minus 1 over m2 square. Why? Because you know, when k is large, okay, in that case what will happen? Your sine square ka over 2 will become or 10 to 1, right? And in that case, when you are going to subtract this value, like we have done here, look at this. When you take sine square k over 2, that value to be 1, you got this. So I'm writing this condition directly there, here, right? Now once you are considering this condition, and if somebody is not able to understand that part, just tell me, I'll be explaining it again. So when you will take it outside the square root, and you will just try to simplify, your 1 over m1 terms will get cancelled out because negative sign will be there, and negative, the second term will become positive. So you will have 2c over m2, right? Now, in this case, your omega negative will be square root. Oh, it's not working. Why it's not working? Let me just write it again. So omega negative is equal to square root 2c over m2. What did you observe from here? Can you tell me? What it is telling you? What it is telling you now? Any idea? So in the starting, when we were talking about m1 and m2, we were saying m1 mass atom is smaller than m2 mass atom, right? So m1 was less than m2. That means in case of acoustical branch, your omega negative is dependent on what? Your angular frequency. In case of acoustical branch, omega negative is itself showing you acoustical. So in case of acoustical branch, the omega depends on just larger mass atom or heavier atom. Did you get it? Is this clear to everyone? Look at this. M1 was smaller than M2. M2 is greater. Means your M2 is what? That is heavier atom. So in case of acoustical branch, your omega depends on just the heavier atom. Done? Clear? Okay, that's great, Snehashish. Okay, now, so already in the starting of this diatomic case discussion, we got to know that we are going to have the two different branches existing. Now, what are these two different branches which are existing here are optical and acoustical. So let's consider this omega versus k relation. Oh, both the lines are not looking straight lines. Let me just try to make it again, and then okay. So in this case, you already observed your acoustical branch earlier, that how the acoustical branch looks like in the 1D monoatomic lattice. Same way we will plot it in this case as well. K 0, then omega is also 0. So this is your acoustical branch, while your optical branch will give you the value here like the graph here like this. Like this. This is your optical branch. Why? Because in the case of optical branch, you don't need more zeros. So at k is equal to 0, the omega is non-zero. Omega is having this value here. Okay? And at plus minus pi by a, it gives you these values. So it's like something like this kind of graph you are gonna have. Okay? Which is not gonna look like... Let me just try to show you how you have to make it. It's a kind of curve, kind of hill, and the other one is something like this. So these two you are gonna get. Okay, like you know about the conduction band and the valence band, right? So similarly we are having these as bands. This is one band, this is another band. So this is going to be the band gap. The gap between two bands is what? It's the band gap. Clear? So anytime if somebody will ask you what is the band gap, so you already know what is the value you will have at plus minus pi by a for the omega positive and omega negative, because you had the two branches in this case. So you will be getting the values here. This is like, you can call it the frequency gap, because the difference in the frequencies you are measuring from here. Okay. And the other one you will have is, if I am going to write, the other one is band width, which is the lower value of that band and the higher value of that band. The difference, that is band width. Okay, this is frequency gap. this is bandwidth, this is bandwidth of above band, and this is for the lower band, right? So I'm going to note down these values so that you will exactly be able to know. And also, if I'm going to talk about omega negative here, it is root C 2C over M2. And this value you will have here is root 2C over M1. And the topmost value of omega positive you had here is root 2C 1 over M1 plus 1 over M2. Okay. At this point, omega was simply proportional to K. This relation which we got here. Here. So it was directly proportional to K. Okay. That's what you are observing. Now, if we are going to talk about the next thing, so your optical branch, can you tell me above one is the optical branch or the lower one is the optical branch? Which one is optical? Above or the lower? Which one is the optical branch? Above one or the lower one? Optical, do you need more zeros? No. So which is not having zero value of omega? This one. Hence the above one is optical. So positive. So its bandwidth is nothing but the root 2C 1 over M1 plus 1 over M2. That's great. Snehashish, minus root 2C over M1. Very good, Deepika. That's great. Okay. Now, same way bandwidth of the acoustical branch, it will be simply root 2C over M2. Why? Because this value is 0. The other value is 0. Okay. So let's write for the acoustical branch. Lower value is 0 there. Okay. Any doubt? If yes, you can just let me know. And frequency gap. What is the gap between these two? That's root 2C over M1 minus root 2C over M2. Right? So this is what we are going to have. Frequency gap is basically between the above and the lower band you got, the difference between the frequencies for both of them. So what is that value? That's your frequency gap. We almost completed this topic now. Just last thing, from this section again there is a chance to get the direct question, because in the previous years, either in NET or GATE, we had, in recent years basically, we had a direct question from this. So I will quickly let you know that part right now. And if after that you want to do 1 or 2 questions, we can take that. Otherwise, we will just end the session here. Okay. So let me just introduce that part. That is something which will help you to decide that how many optical branches are possible and how many acoustical branches are possible in a specific case. So how you will find it? Will you do all this derivation? Then you will get it, but you don't have to do the derivation. Okay. So you can find it without doing the derivation as well. Before going to that part, let me just quickly summarize what we have discussed in the 1D diatomic lattice. We firstly consider the diatomic lattice. We have written the dispersion relation, which had the positive and negative 2 signs in it. And that was helping us to decide whether it is optical branch or it is acoustical branch. How we have observed that part? By putting the K value and by observing whether omega is becoming 0 with the positive sign or non-zero with the negative sign. Other than that, once you got the optical and the acoustical branch, you have worked on finding the long wavelength and the short wavelength conditions related dispersion relations. And once you have done this, okay, you have got the separate expressions for optical and acoustical branches. Then we just plotted them. We worked on finding the frequency band gap or frequency gap, bandwidth for optical and acoustical branches. And you also observed that in case of acoustical branch, in the condition when you were taking short wavelength, your omega was just dependent on heavier atom, means which one was having the more mass, okay, larger mass. So it was just dependent on that. The other one's vibration or other one was not considered in this case, then its mass was not involved. Okay, clear? Now let's consider the next part here, that is how to decide how many number of acoustical or optical branches are there. So when we are going to consider the branch, and we are going to consider the 1-dimension case, 2-dimension case, and 3-dimension case. Okay, so how many acoustical branch you will have and how many optical branch you will have. One more thing, I'm going to take that in the, see how we discussed about it, depending on how many atoms are present in the lattice, right? Is it monoatomic, is it diatomic, is it triatomic, whatever it is. So we are going to consider that it is the p atoms basis or n atoms basis. It's up to you, whatever you want to consider, n atom basis. Or in general, if they will just give you that there are total n, like there are n atoms in the primitive unit cell. N atom basis, when they said, you are gonna work on n. When they will say n atoms in the primitive unit cell, so then you will use n. Done? So both the statements can be given, like any one of them. Both are like the ones you can consider. N atoms basis, you have to work on n. N atoms in the primitive unit cell, you have to work on n. Okay, that's the important point. Now once you consider that part, acoustical branches in the 1D, n atoms basis will be 1. Optical branch will be equal to n minus 1. In the acoustical branch in 2-dimensional case, the acoustical will be 2 and the number of optical branches will be 2n minus 2. In the acoustical, in the 3D case, the number of acoustical branches will be 3 and the number of optical branches will be 3n minus 3. Clear? One more thing. What we have done, we have discussed 1D monoatomic lattice vibration. In that case, how many branches you got? If you will recall the figure, you have drawn omega versus k, you got this, right? This is what? Optical or acoustical? This is acoustical because omega 0 at k 0. So in this case, you just got one acoustical branch. And how many optical were there? 0 optical. So how many atom basis was there? Monoatomic means n is equal to 1. You got 0. Does it get satisfied? Yes. Check for the 2D case and tell me, does it get satisfied according to you or no? That is it giving you the same conclusion what you have got after driving all the expressions? If you are able to get that same, you are getting to know how to use the formula. And if you are getting to know that, whatever question you will get in the exam, you will be able to work on that part. If you will not be able to relate it at the moment, I can show you again like how to do that and how to know about it. Tell me. So, diatomic, but the case was 1D, it was not 2D, so I should not encircle it. The case was 1D, but number of atoms were 2. Same first formula. We didn't talk about 2D, but if anytime they will ask, then you have to go for it. Tell me. 1D diatomic case. So 1D diatomic, n is equal to 2. How many acoustical branches you got? 1. And how many optical you got? 2 minus 1, 1. That is again 1. Does it make sense? And everybody is going to get it? And if they will ask you anytime for 2D, 3D cases and the more number of atoms, then again depending on how many dimensions you are dealing with, you will be able to get that number of acoustical branches, optical branches, whatever they will ask you. Okay? Tell me guys, if there is any doubt anybody is gonna have, we can consider it. But if everything is clear, then that's gonna be great. Okay, we also have some questions, but I think it will be too late. So what we can do, we can try to plan some special session if you guys want to do discussion about the questions or more topics we can discuss there. So you can let me know if you want to have more session, okay, for the question discussion and more topics. So most probably for Condensed, we can plan a special session for this month, while the session here may be for different subjects. We will surely have the sessions here, but for the same subject, we can plan the special session. Okay guys, so we will be keeping it this much right now, and if in case you will be having any doubt anywhere, you can surely let me know. And if you want to get some sample question, I can give you one question too. Tell me. Or if you want to work on the question later on, we can do. Give me a second. Let me just show you one of the questions based on the concepts we talked about today. At least one. Let's take this one. The dispersion relation of phonons in a solid is given by omega square k is equal to omega naught square omega naught square 3 minus cos kx a minus cos ky a minus cos kz a. The velocity of the phonons at large wavelength is. Options are whatever will be the right answer according to you guys, just mention it. Root 3 omega naught a over root 2. Try it now and tell me what is the right answer. Excuse me. Whichever option is correct according to you guys, just mention it. Otherwise, I'm gonna talk about it too in just some time. So basically guys, large wavelength is the main point here. Large wavelength means lambda is large, so k will be small, right? So in that case, what will happen? The cos theta for the smaller theta will be replaced with 1 minus theta square over 2. So kxa square over 2. 1 minus ky a square over 2. 1 minus kz a square over 2, right? So in that case, what will happen? 3 minus 3 cancelled out. Minus minus will become plus. Kx square plus ky square plus kz square will be equal to k square. Have a look at this. So my omega square expression has now become as omega naught square. Then we will have times kx square plus, let me just write it again. Kx square plus ky square plus kz square a square over 2. Now in this case, omega will be simply kx square plus ky square plus kz square can be written as k square. Okay, it is equal to k square. This is like the general expression you can say about x, y, z, and then how you write the modulus of any vector. So that's the thing we are relating here. Omega naught k a over root 2. So when you want to find the velocity of phonons, means group velocity, so d omega over dk, which will be omega naught a over root 2, which is group velocity. Hence your right answer is option D, which is the correct answer. I also have more questions, but the next one, which I was saying, like having the same kind of derivation, will be more time taking one. So I think we should keep it this much right now. Okay, more questions we will try to discuss in upcoming sessions. So let's keep it this much. Thank you so much everyone for joining this session. Keep on doing the revision of whatever you are learning. So when you will keep on doing the revision of the things, you will surely find like it's gonna help you more and more, and you are gonna have much more better command on the things. Today you learned about the topics, concepts and the points, but now to keep it in mind for a longer time, to use it while solving questions, you need to do the revision. So make your proper notebook, keep on doing revision, it will be helping you, right? But without revision, after few days, you will again feel like you don't have much more better command on the topic. So that's what I want to say. Keep on doing revision. It will surely help you a lot to be more confident and to learn the topics this way, right? Thank you so much everyone for joining this session. We will have more sessions in upcoming days, most probably tomorrow as well. We can have early morning session or even at this particular time as we had today in the evening. Okay, also guys, let's keep it this much, and if you are the one or even if any of your friends want to take the subscription to start their preparation under the guidance of top educators, then you can share this information with them too. We are gonna have iconic subscription which will help you to get all the benefits as they have been mentioned here on the screen. You can use and apply the code Anjali A Live as mentioned here on the screen to get the discount in the total subscription amount. Here is the information about the plus subscription, and here is the information about the light subscription. The difference between the plus iconic and the light subscription has been shown here on the screen. So depending on whichever you find more beneficial for you, you can take that subscription. And in upcoming days, so many new courses by the top educators will be starting on Unacademy. So if you don't want to miss these courses and the classes, you can take your subscription and use and apply the code Anjali A Live to get the discount in the total subscription amount. Thank you so much Snehashish. Thank you so much Deepika. Thank you so much everyone. Deepika, morning session, I think again due to some technical reason it's not till now there, but if it will be, then it will be around like you can say 7:30 approx. Okay, so around 7:30 you can check, or around 8 o'clock if you will check. Then later on you can check the recordings of the session if it will be there, or right now you can see. Let me just see whether it has been scheduled or not, because I planned it, but before I started the session it was not there. So I have to just see whether it has been scheduled now or no. Or guys, as you got to know about this session today, similarly you will get to know about that one as well. I can't see it right now. Okay, so it's okay guys, like if it will be there, you can check it out around 7:30 or 8. Okay, like the chances are still less because I can't see the session. Thank you so much everyone for joining the session. And as you got to know about this one today, similarly you will also get to know about that one too if you get some notification or something like that kind of update. So simply for that session also I'll be sharing the information. Okay, don't worry. Otherwise rest, relax, because it's again too late. So rest, relax, and whenever it will be you will get to know. Okay, don't worry about the early morning timings and all. Thank